Hi, welcome to this quantum readiness workshop about building hybrid PKIs and working with key encapsulation mechanisms. My name is Tomas Gustavsson. I'm the Chief PKI Officer at Keyfactor.
And I'm David Hook, VP Software Engineering, Crypto Workshop and Bouncy Castle.
Before we get into the details about hybrid PKIs and key encapsulation mechanisms, we want to say that in case you missed it, we now have standardized post-quantum cryptographic algorithms in the form of MLDSA FIPS204, MLChem FIPS203, and SLH DSA FIPS205. Well, pretty mixed order there, but you get it. So what is important is that the old names that we used to use, which are of course much cooler, dilithium Kyber and Sphinx Plus, those are out and the new ones are in, because we shouldn't mix them up, because MLDSA is not the same as dilithium. But it's definitely a time to celebrate. So this is we've worked in this industry for many years now, and this is the biggest migration we've ever done in the cryptographic industry. So this is celebratory times, and this is a monumental moment. It's something you will tell your grandkids about. You were here when we switched from classic cryptography to post-quantum cryptography.
Okay, so one of the things that's come up a lot with this, of course, is, it's moving to the new algorithms. What does it really mean in terms of how you want to do things in the future? And this idea of crypto agility has been talked about mainly in the context of trying to prepare for the migration. But the other thing that's really becoming obvious is that crypto agility is still going to be required moving on. Now, there's a definition here from a paper that was published in 2021. Crypto agility refers to the ability of an entity to replace existing crypto primitives, algorithms, and protocols with a new alternative quickly, inexpensively, with no or acceptable risk exposure. Those three things are quite important. The thing about crypto agility is it's not just a matter of being able to edit the code and replace one algorithm name with another or an algorithm identifier with another. There is also this issue of expense, risk, and what difficulties are faced by your user community when you do the adaptation. So with replacement, of course, first step is to replace the primitives and keys with the use of new primitives and keys. Really, that is where the excitement begins, though. With signature algorithms, of course, this is fairly straightforward. I mean, signature algorithms fundamentally haven't changed. The only issue that you've got is whether or not you've actually hard-coded the keys you were using in the first place, or somehow hard-coded the algorithms. With key encapsulation mechanisms, however, the process of moving from classical to PKC is actually more complex. Key encapsulation mechanisms are actually quite different to what we're used to dealing with. For example, two-party symmetric key sharing protocols will need to be changed to incorporate a KDF in most cases, and also to deal with the fact that a chem actually generates a secret key internally rather than you providing it with one as you do with RSA, or doing calculations as you would with Diffie-Hellman, where both parties arrive on together. Finally, multi-party protocols need to be adjusted because chems at the moment are all two-party. So being able to use multiple Diffie-Hellman keys, finite field Diffie-Hellman keys together is no longer really going to be an option. Okay, so looking at replacement further, ease of agility usually means a cheaper cost of moving. So a great measurement of whether or not you've actually prepared properly is, how much it's actually going to cost. And costs, of course, are dollar costs, convenience costs, all those sort of things. Moving from classical to PQC needs to consider resource costs as well. So keys, signatures, ciphertexts are all still bigger. More computation is often required. Bandwidth, of course, is going to be something that you'll be using a lot more of too. CPUs that are currently running flat chat will not be able to support the throughput that you're currently seeing. Also, the truth is there'll be new algorithms coming, so the move from PQC to PQC should be allowed for, so that you can take advantage of more efficient and resource-friendly algorithms, because there is still a lot of ongoing development work. Things to think about, of course, is are some assets remote? I mean, if you're trying to change something on a cloud-based server, it's quite straightforward. If the thing you're trying to change is actually on top of a 100-foot pole on the top of a remote mountain, that could be a little bit more difficult. Data migration also needs to be considered, because encrypted data that you've got stored at rest, you will probably need to re-encrypt. Or in some cases, you might just decide to get it off the internet altogether, or at least, protect it some other way so that you're only re-encrypting stuff that you actually need to use. Likewise, there's also the cost of updating key management systems and disposal of retired cryptographic assets. You obviously need to make sure that old keys and old data is disposed of properly. So then with crypto agility, there is the risk aspect as well. Do you have to take systems offline to migrate? What does that mean for your users? Does it mean they're going to not have access when they need it? How do you manage that? Okay, you take something offline to upgrade it. What happens if it comes back up and it doesn't come back properly? What do you do if there are issues? Do you have some incident management response in place? How many migration processes that you've got can you actually involve automation? I mean, there'll be a lot of certificates to update, for example. This is clearly an area where tools will help. Will any of the migration processes create a security risk in themselves, and how can those risks be mitigated? Ideally, it wouldn't be turning off encryption temporarily, but yeah, the reality is that while stuff's been taken offline and brought back online, there might be gaps, there might be data written to disks that you may not be aware of. There might be a whole bunch of things like that. If you're not monitoring all that carefully, there may be stuff left around after a migration has taken place, which could create problems, not to mention the actual issues with the migration itself. And finally, what are your third parties doing? So are any of these on the critical path for migration, and will they be ready in time? It's not just you, most likely, that is actually managing your cryptographic assets. You'll probably have third-party applications which are actually also involved in this by proxy. They also need to be updated. Okay, so one of the migration mechanisms that's been put forward is the idea of hybrid certificates. So the concept here really is that they're dual key. Most of the mechanisms that are provided in the context of hybrids are actually there to allow you to introduce the post-quantum key into your system without actually having migrated to it properly. So they're really what you call a forward provisioning mechanism. There's currently 4 different approaches of this, which are all in different stages of standardization. The one that is most standardized at the moment is a system that was previously known by Catalyst from the company that originally developed it, and that was standardized in X509 in 2019. There's several new standards. One is Delta, which is also known as Chameleon, which is a draft in the IETF process. There's Composite, which is another way of providing multi-algorithm support, but via the declaration of a new algorithm. So it doesn't quite have the backwards compatibility aspects that Delta and the X509 standard do. And it's also in draft, although some bits of the Composite idea are actually coming out of draft at this point. And then finally, there's a concept called related certificates, which is another IETF draft. And it's not actually dual key, but it does actually give you a mechanism for marking a particular post-quantum certificate as being related to an earlier certificate that you may not be able to reissue rather. So that's also in draft in the IETF, and that's also managed via extensions. Now, with backwards compatibility, as I mentioned, Catalyst, Delta, and related certificates are all extension-based, and the use of the extension-based mechanism means that fundamentally, as long as the extension is marked non-critical, you should find that it's ignored by whatever you're giving it to. Now, Catalyst allows for the addition of a second public key and a second signature. The Delta approach, actually, the extension provides a template basically for constructing a new certificate using the carrying certificate. And the template in the extension actually allows you to fully specify a completely different certificate to the one that's actually carrying it. And then finally, related certificates, as I said before, basically the idea there is that they establish a relationship between the new certificate and the old certificate. So the kind of issues that we've got at the moment, and this is due to the fact that things are in a state of flux, only Delta and related certificates include attributes defined for use in certification requests. So these are the the only two that actually have a standardized mechanism for providing certification requests. There is a certification request attribute for Catalyst, but it relies on a definition. Well, what we're currently using relies on a definition in what's known as the Tchaikovsky draft, which was the original Catalyst proposal, the ITF, which has now expired and hasn't come back to life. On the other hand, Delta and related certificates are actually still in draft themselves, so it doesn't really matter which way you go, you're basically stuck using a draft in some aspect. Now, Composite also requires the implementation of new public key and algorithm types. So with a composite certificate, you can't just send it to a device that's got no idea it's coming. You really have to have upgraded the software on that device first before it can make effective use of it. The other thing too about all these mechanisms is they really are designed for transition. If these certificates hang around for too long, they do have the potential, possibly due to malfeasance or just minor bugs in the way the migration was handled, to actually be used in a downgraded tech. So ideally, you'd make use of these while you need them, and then you'd actually move to regular certificates with single keys.
Now we'll look into how this specifically relates to PKI and signing. And I'll start by looking at some of the protocols and the cryptagility aspects that these have. You know, these protocols are things that we've been using now for a long time, and you can see some, how they will cope without significant changes, you could say. So we put a green checkbox on the CMP, or a certificate management protocol, which handles, plain signatures and small data. And the interesting thing is that, which we'll talk more about later, is that it has the capability of using the CRMF certificate request format, which actually can handle key encapsulation mechanisms. It can also do PKCS 10 CSR, so it's quite very flexible and agile. Then we have EST, which is somewhere in between, I would say. It uses TLS and plain signatures on fairly small data, which makes it agile enough for moving to post-quantum algorithms from that aspect. The only downside is that it relies on PKCS 10 certificate sign-in requests, which today require signatures, which is something that key encapsulation mechanisms cannot handle. So it's not perfect. It's not bad, but it's not perfect either. And then we have SCEP, which is a fairly popular protocol in a lot of instances today, which does both signing and encryption in a way that typically relies on RSA keys today. So, which will be quite hard to move over to using post-quantum cryptographic algorithms without significant changes to the algorithms. So, it might be good to look over or protocol usage for solutions as you go forward during the cryptographic migration. And if we look at hybrid PKI, there is, as David mentioned, currently only one standard out there, which is the X509 alternative keys and signatures. But as David mentioned, X509 doesn't specify a certificate signing request. So how to request a certificate? You can get a standard certificate, but it's hard to request if you don't have a request format. Then, of course, we have implemented the draft Tchaikovsky, as David also mentioned, by a command. So we can generate these draft CSR at least and process these. So considering the, say, almost fully standardized approach here, there are likely some dragons, lingering in the bushes here. So, and of course, we want to encourage viewers of this who will be the first to submit a pull request to our EDBCI Easy REST client to handle hybrid CSR, which it doesn't do today. Shouldn't be a big change, though. So, with all that as background, I think it's probably worth just taking a bit of time to have a look at the current state of play. As Thomas said at the beginning, we've just gone from the fairly coolly named Kyber dilithium and, Sphinx Plus, to the official MLChem, MLDSA, and SLH DSA.
And as Thomas also pointed out, it's very important to realize that those final standardized algorithms are not the same as Kyber dilithium and Sphinx Plus. So if you're going to be using them, make sure the implementation you're using is MLChem or MLDSA or SLHDSA. Now, the other thing that's going on, of course, is round 4 is currently drawing to a close. So round 4 was an extra round that was started to select another key encapsulation mechanism. Basically, it's now between two algorithms, one called BIKE and the other one called HQC. There's a third algorithm that's also in the round, Classic Michelese, but it looks like it's going to be standardized outside of the NIST process anyway. The question really, I think, for NIST really at the moment is more whether or not they're going to join in with their own standard or just refer people to the other one. The other thing, of course, too, is that there is a fourth signature algorithm that's not in this slide called Falcon. And there should be a draft standard for that coming out about the same time round 4 is closing. So further to this, and just going back to the comment I made before about PQC to PQC migration and the need for crypto agility for that, there's another signature round that's currently taking place. It's got 40 candidates, 30 of them are still standing, 7 of them are lattice-based. Some of them are smaller, some of them might be more useful, some of them are interesting. NIST is going to be announcing the next round of that sometime around the end of the year as well, apparently. But yeah, it's just further evidence so that, there's a lot of work still going on in this area. So even though we do have 3 fairly good standards right now that we can use today, it's important to keep in mind that you may want to move to one of the other ones later. And for example, there's a variant in the process of Sphinx Plus, which is actually based on ASCON, which was the winner of the lightweight encryption competition. So for small device people, this particular signature algorithm could be quite useful in terms of the fact that if you've implemented ASCON, you can actually then provide a PKI mechanism on top of it. I assume because it stands up securely, but at the moment there's no reason to think it won't. And the other thing that's going on, of course, is with new algorithms, we need new public key formats, new private key formats. The public key formats are pretty much decided. There's still a few conversations going on about how private keys should be done. And the IETF drafts that are going through in the process, which will document this, are currently getting finished up right now. And yes, of course, as we mentioned before, X509 actually includes the alt extensions, but lacks a standardized CA mechanism. And there's all these other IETF drafts which are going on. Certificates, cryptographic message syntax, there's quite a good one for using key encapsulation mechanisms now in CMS. There's various approaches, of course, certification request management and various things like that too. So a lot of standards and revised standards coming out.
So before we dig into showing what you can do, we'll just briefly mention the quantum-ready solutions of Keyfactor. So we have basically a full suite of PKI and cryptography-related tools. We have Keyfactor command that can do inventory of your existing certificates, so you know what you have. And on the other hand, help you automate replacement of certificates. And then, of course, we have the Bouncy Castle cryptographic APIs, which is hence David here, which implements all the nitty-gritty details, the algorithms, everything we need to build things like EDBCA on top of that to issue certificates, and sign server in order to issue or to sign artifacts using, of course, the post-quantum algorithms.
Basically, in the Bouncy Castle case, we've actually got support now for all the NIST standards. There's a beta that's currently available, and hopefully we'll have an actual proper release out in the next few weeks. We're currently doing algorithm testing with the NIST ACVP system, so we're fairly confident the implementations themselves are right. We've done interoperation testing as well on the public key certificate side of things, thanks to the IETF hackathon group. And we've got private keys encoding, but it remains to be seen whether that will be the ultimate way that they'll encode. We'll probably move to using a seed-based mechanism, though, for the final release in the case of ML-Chem and ML-DSAs. That seems to be where it's all heading now. We do have support in place for the different hybrid alt mechanisms. Delta and Chameleon are also supported, as is Composite. And we're currently in the process of adding some certificate binding support too. The only real issue with certificate binding is they still haven't allocated the OIDs for that, so we're probably going to have to use an experimental OID for that at the moment. You need to wait until the actual standard is ratified before actually trying to use that in production. Then finally, we've done updates to cryptographic message syntax, so there's already support for the newly released Chem recipient info structure. That's allowed us to actually do additional updates to the certificate management protocol, certificate request message format as well, which take advantage of the fact that the Chem recipient is now in place. And we're also in the process of adding some of the TLS cipher suites which have been proposed just in draft as experimental.
And that brings us to our demos, where we're going to try to show a couple of these things that we're talking about, and see that it's not only talk, that you can start doing things for real. And I mean, one thing that is really interesting and fun and important is that with the standardization of the algorithms, you can actually start to use things in production. Because now we had several years where we had proof of concept and things with the draft algorithms, but this was always not for production because it's going to change and you will have to throw everything away. But if you do something with ML-DSA or ML-Chem today, it's going to be interoperable and it's going to live for many, many years. So, of course, the only snag right now is that while the standards are here and we're implementing it, 859 is done, there is a very huge ecosystem, of course. There's TLS, CMS that we already mentioned, and different providers and vendors and implementations are still in a bit of a flux. But give it a couple of months more and we'll surely be in a much better position. We'll actually see a little bit about this in the demos. So what we're gonna start with in the demo is to create a post-quantum hybrid PKI, which means, of course, a PKI which uses a hybrid certificate, the X509 alt key and signature hybrid standard, using one classic algorithm, EC-DSA, and one post-quantum algorithm, ML-DSA. And the only thing we need before to get started is an EGBCA container. And with that, we will create a CA hierarchy with a classic, CA setup with a root CA using a higher security level, and a sub-CA using slightly smaller keys, and then finally an end entity, which will be the next phase of the demo. So here we will go into the demo. So here we have a branch of EGBCA 9, which will come later, which will be the upcoming release that supports eventually the final standards of ML-DSA, etc. You can see here that I started what we call TLS setup simple, which gives you a warning, a security warning there, which is just a nice way to tell you that if you're going to production, it will be things to do. So I'll do in a non-production setup here. So the first thing we have to do is create what we call a crypto token, which is where we generate the keys in EGBCA. So first I will create a crypto token called PQC root. It will be software keys only, no HSM here so far. And I create the crypto token and it's done. And then I will generate keys on the crypto token. For the root CA, I will generate 2 keys, since it's going to be a hybrid. And we'll use NIST security level 256-bit on this one, which means a classic signing key of ECP2521. And we also need to generate a test key for this. This is just an internal EDBCA thing in order to make sure things are running. And we will generate what we call a default key, which is just an internal key. It's actually not going to be used, but it has to be there for things to be created as we want. And finally, we will create our post-quantum key, where we will use MLDSA 87, which is the level 5 of MLDSA after this competition. So that's it. Now we have our keys for root CA. We will do the same for the sub CA. Create a crypto token for the sub CA. And once that is done, we will create a signature key. In this case, we will use P384 for the sub CA. And just as for the root CA, we need a test key, which is just used to do some internal tests. We also need a default key, which will not be used by this CA, but it's needed. And finally, we'll create our post-quantum key, where we'll use MLDSA 65, which matches the security level of P384 of ECDSA. So now we have our keys created for our CAs. With that done, we can actually move on to create the CAs. So here we see we have unused crypto tokens. So now we'll put them in use by creating 2 CAs, of course. First, we will create our root CA. You see root, I will call it. I will select the crypto token I just created, of course. And the signature algorithm, the classic signature algorithm, will be SHA-512 with ECDSA. So it automatically, friendly enough, selects the assigned key P521 for me. So as for the hybrid, I will select the signature algorithm MLDSA 87 because now EDBCA recognizes that I have only an MLDSA 87 key on this crypto token. I will finalize with giving this CA validity. That's all I need to do. I can, of course, specify a lot of other fields, but for a simple root CA, this is enough. It will be kind of best practice contents of the certificate. Now I will create a PQC sub CA. So the only difference here, of course, is that it will be assigned by the root CA. I will use the sub CA crypto token. I will use SHA-384 with ECDSA, and hence it selects my signed key P384. And as a alternative signature algorithm, I select MLDSA 65, which of course goes together with my signed key MLDSA 65. Now there's a little bit more to do. Instead of a self-signed CA, I will say that this will be signed by our PQC root. And I will give this a slightly shorter validity of 1 year. You can easily select this and create, and it's fast. Of course, cryptography is fast. So now we have our CAs. And we can go in and look at the CA certificates in the CA structure and CRLs. So we can see here on the PQC sub, for example, you can view the certificate. And when we look at this, we see that it has 2 keys, one EC, P384 key. It's of course signed by the root CA. And it has the alternative public key of MLDSA 65. Here we print out the supposedly NIST security level of 192 bits. And we also see that there are 2 signature algorithms. One classic, which is a standard certificate signature algorithm, SHA-512 with ECDSA, because it's signed by the root CA. And the alternative signature algorithm of MLDSA 87, also from the root CA, which had those keys. So that's how easy it is to create a hybrid PKI with MLDSA or with ECDSA and MLDSA. And of course, there are other algorithms that you can select. Now, with our hybrid PKI created, we can move on to create an ML-Chem end entity certificate. And this we will do using CMP, or Certificate Management Protocol, that we talked about earlier, and ML-Chem, which interestingly enough is unable to create a classic proof of possession. For those who don't know, proof of possession is a structure used in certificate signing requests, where you take the certificate signing request containing the public key and sign it with the corresponding private key. And this enables anyone who receives this CSR to verify that whoever created the CSR is in possession of both the public and the private key. So you're not sending a CSR with someone else's public key in it. So this is very useful. And but with ML-Chem, we have to do it in a slightly different way that we're used to. So the starting point is, of course, our EDBCA container started with our post-quantum hybrid PKI created. And we will use the EDBCA CMP client, which is a tool that comes with EDBCA, to run our CMP protocol. And what we'll do, briefly overview, we will create a CMP alias, we will create an end entity in EDBCA, we will create a CRMF request, requesting indirect proof of possession. We'll mention that a little bit more in detail. We will issue the certificate from the CA using CMP. And the indirect proof of possession means that the certificate is actually sent back encrypted to the client. So the indirection here means that, well, if the client is able to decrypt the certificate, then the client has proven that he is in possession of the corresponding private key. So that is done when the CMP response is received and the issued certificate decrypted. So let's jump into the demo. In order to issue a certificate with EDBCA, we need to create what is called an end entity. So we start by creating an end entity. So we go to RA functions, add end entity, and maybe embarrassingly enough, I will not use a very production-ready setup here. So I will use this pre-installed empty profile installed. Of course, in a real environment, you would create your new end entity profile containing only the fields you need, etc., etc. But for the sake of keeping the demo short enough, I will use the empty one. There are lots of tutorials how to create end entity profiles. So I will create an end entity called CMP Inc Cert and give it a one-time enrollment code. I will use the same common name as the username here. Let's map this actually. So I copy the field and paste it in there as a common name. So we'll make a very simple end entity with only a common name. And then we can scroll down and select the CA. So we'll issue, of course, from the post-quantum sub-CA. And we will use user-generated keys, which we will do from our CMP client. So with that end entity added, we also need an endpoint for CMP. So this is done in EDBCA by creating a CMP alias, because you can configure multiple CMP endpoints with different configuration and different policy. But here we will add a CMP alias in client mode, which we will call it CMP, which is a default one. We will use HMAC authentication using the one-time enrollment code. We will use use the CEnd to map the request to the end entity we just created. And we'll just keep this CMP endpoint simple and don't need to return so many additional CA certificates and such. So if we save there, we have our CMP endpoint created. And now we can move into creating the actually end entity certificate, which is the very interesting part in this demo. Okay, we switch over to our CMP client, which is a tool that comes with EDBCA. It's called CMP client.sh, and we have a nice command line here in the command line, we say that we give the command crmf, which means that we will create a crmf request message. Of course, we pointed to a URL, which is our CMP alias that we just created. We provide the CMP encert common name, the same as we added with the end entity. We give a password, which is for the HMAC authentication, and we say that it will generate an MLCAM 512 key, which will be the requested key encapsulation mechanism. And we'll give the flag to say include POPA, which is include proof of possession, which then, of course, will create this request for an encrypted proof of possession. So running a command, it goes fast. So it first prints out a bunch of things about the request, but it specifically says that it added proof of possession of type 2 encert, which is something you can find in RFC 4211 if you want to study it in detail. And it goes on to say that it uses a CMP URL and writes the certificate to a destination directory. And interesting, of course, is that we specify here that decrypting returns certificate with private key of type MLCAM 512. This is the CMP client just saying that, okay, I received an encrypted certificate back and I decrypted it with my public key. With the private key. And then, so the request was successful and we received a certificate. So we can try to look at the certificate we stored. To do that, we switch over to another tab that we have with OpenSSL. So I have installed an OpenSSL with the OpenQuantumSafe provider, which is currently a provider to allow OpenSSL to perform some quantum or to use some quantum safe algorithm, post-quantum algorithms. So if we look at the certificate I just received from the CA, with OpenSSL, we see there's a bunch of extensions, which are the extensions that David talked about for being a hybrid certificate. So these are all, of course, by the CA. So that's since the CA is hybrid, the end entity certificate will be a hybrid certificate as well, which means it's signed by both keys of the CA. Secondly, we can see that it's, of course, issued by our PQC sub-CA. It has the correct subject DN. And the public key algorithm is actually the OID here for MLCAM, the official NIST-issued OID for MLCAM. But we also can see that OpenSSL is not able to parse this. So this is where we talked about a bit earlier that things are currently in a state of flux. So if you want interoperability, so we're testing interoperability, but tools are right now in a bit of varying state of implementation and understanding the, say, hybrid OIDs, the NIST final OIDs of the algorithms, etc. So in order to get everything interoperable between different vendors or different tools, it can be quite tricky. I will show an older certificate that I issued that we can parse with OpenSSL with the OQS provider. This is actually an older certificate that I issued based on the draft specifications of the algorithms. And in this case, OpenSSL claims that it's signed by MLDSA 44, but it's actually a draft version of this standard. So at least the branch of OQS that I found could not handle the final updates, but could handle the draft updates. So this is, you could say, interesting experiments, but give it a couple of more months, and I'm sure that everything will be quite smooth. So that was a demo of proof of possession for chems. So code for this, for Bouncy Castle, is available in something nicely named as the PQC Almanac, which shows how you can do this in code, which we'll dig into a little bit as well. But just a summary of what we have done. So we generated a CRMF request with an MLChem public key and requesting proof of possession of type key encipherment and pop of private key subsequent message enquery search. So this is all things taken from the RFCs, like RFC 4211. And what happens when the CA receives this request is that it will issue the certificate but encrypt it in the form of a CMS message and envelope data. And it will encrypt it with an AES key derived using the MLChem public key of the request. So then the client will receive the CMP response and find out that it's an actually encrypted envelope data, a CMS message, and it will decapsulate the AES key using its MLChem private key, and eventually then decrypt the CMS envelope data, retrieving the actual certificate. So this is all the steps that we did. And now David will talk about how it's actually done.
Yeah, so having seen how it actually works in the EJBC UI, it's interesting to have a look at how it actually gets written under the hood, so to speak. If only just because it actually shows use of some of the new features of CMS for supporting chems. So in this case, basically, we've just got the generation, first 3 lines of the generation of the MLChem key pair. We're using MLChem 768, which is the mid-range parameter set. We then do something unforgivable to generate the certificate request ID, but that's okay. We'll deal with that later. Maybe don't do it like this if you're doing it at work, though. This is used to actually build a certificate request message builder. And then we actually go on to add the public key identity information, and then we specify the EncCert protocol, which Thomas mentioned before. And that tells the CA that what we're expecting is that it will send us back an encrypted certificate, and we'll respond to that with a hash of that certificate to prove that we actually understood it, thus satisfying the proof of possession requirement, showing that we've got the private key. Continuing with the client side of the transaction, having sent our certification request message off to the CA, we get back a certificate rep message as a response. The next thing we're able to do is we can confirm that that actually has the encrypted certificate in it, which is what we're expecting, so we can tell the CA has correctly implemented cert-encrypt protocol. Now, for getting the encrypted certificate out, we need to create an enveloped recipient which actually uses a chem key. So we have the JCE chem envelope recipient here, which is constructed using the chem private key for the public key that we've been requesting the certificate for. Our next step, what actually happens under the covers, is that we basically, the chem private key is used in the recipient to extract the shared secret from the encapsulation that's carried in the CMS message that's enveloping the actual certificate. That recovers the RSA session, the AES session key, which is then used to decrypt the certificate and return it to us. Then finally, the last step in this particular slide is we're just verifying that the certificate is actually valid for the CA that we've actually requested it from. And one thing which is not shown on the slide, what we would do next is we would then send back a message to the CA containing a hash of the certificate we just decrypted, which would allow the CA to actually verify that we have proof of possession and then allow our certificate to be published by the CA. So Thomas mentioned earlier there was a PQC Almanac. The full details of this protocol as described in the code here are actually in that too. So if you're interested in these things, I'd definitely encourage you to download it and have a look.
And finally, we would just like to mention the Keyfactor PQC lab, where you can stay up to date on the latest innovations from Keyfactor and easily, for free, set up your own lab environment in Azure or AWS with trials and open source software. and there's plenty of educational resources on our PQC lab. And this concludes our workshop. I hope you enjoyed it. Thanks for sticking with us all this time. Hope to see you next time.
And thank you, and yes, don't forget to download the almanac. Cheers.